Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to learn how to write momentum equations in two-dimensional impacts. So in this example, focus on this picture right here. We have two cars. This is a picture, imagine an instant before an impact, where this green car is moving, we'll say southward with a velocity of 15 meters per second, and that's the velocity I call VG1 for velocity green car picture 1. The blue car is moving east at an unknown velocity that I called VB1. Right. Now imagine that these cars impact and move off as one mass in such a way that their velocity vector that I've called V2 makes an angle of 25 degrees with the positive x-axis here, or the direction, I guess, east in a north-south, east-west sense. And what we're going to try to calculate from this information is VB1. How fast was car 1 moving? So when dealing with impacts, momentum is a concept that's almost always important. Key concept here is that as long as we consider this our system, the forces between those cars would be an internal force to the system. That's going to allow us to write a momentum conservation equation. Now remember, momentum is a vector quantity, so we apply it by direction. So first equation I'm going to write is this: conservation of momentum I'm just going to give a direction to call positive. We can call that the positive x direction. Just indicating a positive direction is good enough. So we look at our picture here before the impact. We're going to have one momentum term only. The blue car has a momentum equal to mass of the blue car times VB1. That momentum would be positive because the velocity points to the right. The green car doesn't have a momentum in this direction. We could put a 0 here if we wish, or we could just leave it blank. All right. Now we're going to take a look at the momentum after the impact. So the momentum vector after the impact will have a magnitude, let's see, mv. The m is going to be the mass of the two cars. So mass of the blue car plus mass of the green car times v2. This expression would give the magnitude of the momentum after the impact. However, we're looking for just this component of it, so that needs to be multiplied by the cosine of 25 degrees. So we're going to have mass of the blue car plus mass of the green car times v2. Cosine 25. So this is the magnitude of the momentum after impact times the cosine of 25 degrees gives us this component of the momentum vector after impact. And again, we can put equality because of how we're defining our system. We're defining our system as both cars together. So the force of impact between these cars would be an internal force. Now, in this example, we're going to imagine that these cars are identical cars, which would mean the mass of the blue car and the mass of the green car would be the same. But it doesn't have to be. Oops. In a lot of examples, these would be different masses, and I went ahead and wrote the equation demonstrating how we would write it as if they were different masses, but I'm going to proceed with the rest of this assuming they're identical cars. Now, if they're identical cars, that means this can be written, I'm just going to call this mVB1 equals 2m v2 cosine 25. And you'll notice that the mass is now going to divide out of this. And let's see, VB1 equals 2 V2 cosine 25. This still has two unknowns. Don't know VB1, don't know V2. All right, so we got to write another equation. Momentum, remember, is a vector concept, which means we can apply it by direction, just like a Newton's second law equation. So I'm going to go ahead and write another conservation of momentum equation with down the positive direction for our momentum. Then I look at my original picture and I see that the only momentum vector is the green car. So we're going to have mass of the green car times VG1, and that's going to be positive because the velocity points down, and I've got down positive. The blue car does not have a momentum vector in this direction. If I wanted to, I could put a plus 0 here. I guess I'll go ahead and do that. Right. Now, equals, now I'm going to look at the momentum of the system after impact. The magnitude of the momentum is going to be, just like it was before, mass of the blue car plus mass of the green car times V2. This would give the magnitude of this momentum vector, whether they were the same masses or not. And then I'm just going to multiply by sine of 25 degrees so that I'm getting this component of that momentum vector. Now, just like I did before, I'm going to make use of the fact that in this problem they're the same masses, which means this can be written Vg1 equals 2 V2 sine 25. And that's because if this is m, this is 2m, and the masses just divide out. All right, so this is a known value here. This is an unknown value. We could go ahead and find V2, but V2 is not really what I was looking for. I'm looking for VB1. So what I'm going to do here, I'm just going to play a little math trick on this. I'm going to go ahead and I'm going to call this equation 1 and this equation 2. And what I'm going to do is, keeping in mind that I want VB1, I'm going to take equation 1, divide it by equation 2. If we do that, we're going to have VB1 over VG1. Right, that's going to be this divided by this. And on the right, we're going to have this divided by this. And I'm going to go ahead and write that all out without the masses, though. So that's going to be 2V2 cosine 25 divided by, now I'm looking here, right here, 2V2 sine 25. And you notice the 2's are gone, the V2's are gone. And all we have here is I guess that's cotangent. I'm going to go ahead and just write it cosine 25 over sine 25. So VB1 is going to equal VG1, and I'm going to go ahead and just put a number in now. 15 meters per second times the cosine of 25 degrees over the sine of 25 degrees. I'm going to go ahead and calculate a value for that. And I got about 32.2. I'm just going to put approximately 32 meters per second. So, I hope this example demonstrates how to write momentum equations in 2D reasonably effectively. I just kind of want to highlight the big ticket examples here. You always draw a picture of the system before the impact. Include velocity vectors and write down any vectors that you know. Give names to any velocity vectors you don't know. Draw a system or a snapshot of the system after the impact. Include a velocity vector. Label it something like V final or V2. For momentum problems or for impacts, write momentum equations, and you can do so by direction. Here I started with conservation of momentum to the right, and make sure you dictate which way you're calling positive, because remember, momentum is a vector concept, so it follows vector rules for plus, minus, right, left, that type of thing. In this case, we can write one for the horizontal direction, one for the vertical direction. Momentum equations are typically easy to write, mass times velocity, mass times velocity. However, here we had to keep in mind, because we're looking at a specific component, that's why the cosine 25 is here. Same thing with the sine 25. Usually you end up with equations reasonably easy to solve, at least if they're not elastic type of impacts, and I'll save that for another video. Have a great day.